Welcome back to the deep dive. Today, we are taking on a topic that sits right at the absolute center of safe anesthesia practice.
And, maybe more importantly for you, right at the center of your MD anesthesiology examination preparation.
Exactly. We're going to be dissecting the intricate, multi-layered safety systems of the modern anesthesia machine.
And this is so much more than just academic knowledge. You have to think of this as the engineering blueprint of patient safety.
Right.
And for the exam, it's a massive topic, a really high-yield one that, it routinely appears as a major 20-mark question.
And we've seen that pattern, haven't we?
We have. If you look at the DNB questions, I'm thinking June 2012, June 2013, April 2016, the examiners consistently, and I mean consistently, demand a detailed list and functional description of these systems.
Specifically the ones designed to prevent what?
The delivery of hypoxic gas mixtures, that's the big one. So your ability to give an organized, really comprehensive answer here is just paramount to your final success.
That immediately frames our mission for this deep dive, then.
Yeah.
We need to go way beyond just a simple list.
Absolutely.
We need to explore the engineering principles, the operational caveats, and even the specific ways they can fail. So what's the core purpose? What are these systems actually designed to do, and what errors are they trying to prevent?
The foundational purpose is stated very clearly. The prevention of an intraoperative anesthesia accident and related severe injury.
Okay, that's the big picture.
It is, but on a micro level, the systems target four main categories of, catastrophic error. First, and most important, they prevent the delivery of a hypoxic gas mixture.
The most common and dangerous one.
By far. Second, they prevent the wrong gas from being delivered at all through indexing. Third, they manage pressure failure from the supply line.
So stopping the flow from just cutting out suddenly?
Precisely. And fourth, they safeguard against leaks and pressure excesses within the breathing circuit itself.
It's just fascinating to me how far back this commitment to safety actually goes. It really grounds the whole discussion when you think about the history.
Oh, absolutely. You must always start by acknowledging the foundational work. People like Sir Frederick Hewitt.
Over a century ago, right?
It was. He recognized the inherent danger of just combining N2O and air. He realized it created an unacceptable hypoxic mixture.
And that intellectual leap is everything.
It is. The understanding that you have to guarantee adequate oxygen, not just assume it's there, that led him to design some of the very first apparatus to deliver oxygen and nitrous oxide in variable proportions.
So that historical need is the direct ancestor of every modern hypoxic guard we're about to talk about.
It is the direct philosophical origin, yes.
Okay, so let's talk structure.
Yeah.
For that high-scoring answer, you can't just throw out a scattered list of features.
No, that won't get you the marks.
You need a professional, logical framework, one that sort of mirrors how the machine actually works. How should we logically classify these safety systems?
The perfect answer needs that structural integrity. It has to map the gas flow from the wall or the cylinder through the machine and then finally to the patient circuit.
Okay.
So we'll structure this deep dive and your exam answer around 6 major functional areas.
Walk us through that map.
We'll begin with gas supply safety. This covers all the passive indexing systems at the machine's interfaces, so cylinders and pipelines.
The first point of contact.
Exactly. Next is flow control safety. This deals with the mechanisms that regulate and mix the gases, especially N2O and O2.
The mixing chamber, essentially.
In a sense. Third, a critical subset, oxygen-specific safety. These are devices that react only to a loss in O2 pressure.
Got it.
Fourth, we'll analyze vaporizer safety, which is all about accurate delivery of volatile agents and preventing cross-contamination. Fifth, breathing systems safety managing the integrity, flow, and pressure right at the patient connection.
The final step.
Almost. And finally, alarm systems, which provide that electronic detection and warning layer over everything else.
That's a very clear roadmap. Let's jump straight into that first stage then, preventing the wrong gas from ever getting into the machine in the first place. So, gas supply safety. This is all about indexation and identification.
It is.
Because if the wrong gas gets connected at the source, every single safety system after that could be compromised. The core idea is non-interchangeability.
That's exactly right. And for the exam, you aren't expected to be able to rebuild these components from memory.
Of course not.
But you must show that you have a conceptual understanding of how these passive mechanical defenses enforce that specificity.
And we start with the simplest, but often the most effective layer, just looking at it.
Visual coding. The color coding of cylinders and pipelines is the universally standardized first line of defense.
And its purpose is purely visual identification.
Purely. It's to prevent the accidental connection of the wrong gas source. Oxygen is white or green, nitrous oxide is blue, air is yellow or black and white.
It's a global standard?
It is. And it's often reinforced by labels, of course. But the color is the immediate cue. Now, a good candidate should also point out that, while it's simple, relying only on color is inherently vulnerable to human error.
Distraction, fatigue.
Precisely. Which is why you need the mechanical safeguards.
And that brings us to the key mechanical safeguard for cylinders, the Pin Index Safety System, or PISS.
Yes.
What are the mechanical specifics here that make it non-interchangeable?
So the Pin Index Safety System, PISS, is the critical mechanical guard for the small cylinders that connect via the yoke assembly.
Right.
The whole mechanism relies on a fixed, very specific arrangement of two small pins that stick out from the yoke assembly.
And they have to line up perfectly.
Perfectly.
Yeah.
With corresponding drill holes in the cylinder valve outlet.
And can you give us the high-yield configurations, the ones we absolutely need for the exam?
Yes. You must know these. The positions are standardized, 1 through 7. Oxygen is indexed at positions 2 and 5.
2 and 5 for oxygen.
And nitrous oxide is indexed at positions 3 and 5.
3 and 5 for N2O.
Because that pin configuration is totally unique for each medical gas. A cylinder of N2O literally cannot be physically clamped onto an O2 yoke assembly.
It's a physical passive guarantee.
It is. It protects against human installation error. The force you would need to cross-connect them would actually damage the yoke or the valve. It provides physical resistance before a catastrophe can happen.
And what about the seal? You've got this high-pressure connection. It needs to be airtight.
That's where the Botox seal comes in.
Okay.
Its conceptual safety role is crucial. It's a non-flammable, deformable washer that maintains an airtight, high-pressure seal between that cylinder valve and the yoke.
And for the exam, you need to know what happens if it fails.
You do. If the Botox seal is missing, or it's split, or just put in wrong, high-pressure gas will leak out.
A loud hiss.
A very loud hiss. And that rapid leak doesn't just waste gas. It can lead to the rapid and premature exhaustion of the cylinder supply, which is especially critical if it's your only O2 source.
Okay, so we've covered the small E cylinders. What about the larger cylinders, or more commonly, the pipeline sources coming from the hospital wall?
For the large cylinder valves, which are screwed directly into the machine, we use the non-interchangeable screw thread system.
So different mechanism.
A different mechanism, same principle. This indexing relies on gas-specific differences in the diameter, the thread pitch, and the connection size.
So an N2O valve just won't fit an O2 port.
It just won't. The threading geometry is different. It operates just like PISS, but with threads instead of pins.
And for the pipeline supply, the wall outlet.
That is handled by the Pipeline Diameter Indexing System, or DIS.
DIS.
And DIS is mandatory for all the low-pressure connections, usually around 50 psi at the pipeline inlet.
Where the hose from the wall plugs into the machine.
Exactly. And DIS uses combinations of distinct, non-interchangeable threaded connections and nipple diameters. Its whole purpose is to prevent you from connecting the machine's oxygen hose to, say, the vacuum port or the nitrous oxide outlet on the wall.
So all these systems together, PSS, DIS, screw threads, color coding, they guard against that fundamental error of misidentification at the source.
They do. They prevent cross-connection right at the periphery of the machine.
Okay, this transition moves us from the outside of the machine into its internal workings. Specifically, the systems that guard against the most critical operational failure you can have, loss of supply pressure.
Absolutely. And this area is consistently, and I mean very consistently, highly tested.
This is where the machine shows its autonomy and its redundancy.
Exactly. And we start with the pressure reduction systems.
Tell us about the pressure regulators.
Okay, so pressure regulators are absolutely essential for functional safety. Their purpose is to take that extremely high and variable cylinder pressure.
Which can be up to, what, 2,200 psi for an O2 cylinder?
Easily. And it reduces that down to a safe, constant working pressure, which is typically maintained between 45 and 55 psi.
And that constant pressure is vital.
It is, because all the internal machine components, like the Flowmeters and the proportioning systems, they're calibrated and designed to work reliably only within that very narrow pressure range.
So a failure of the regulator could damage things.
Or cause flow to fluctuate wildly. If it fails to reduce the pressure, you could damage components. If it fails to maintain it, your flows are unreliable.
Now, on to the critical oxygen failure safeguards. These are mandatory in all modern machines. How does the machine actually detect and then react to a drop in oxygen supply?
We have two highly integrated systems here. The first is the oxygen supply failure protection device.
Okay.
This device's sole purpose is to interrupt the flow of all other non-O2 gases. So your N2O, your air, when the pressure of the oxygen supply drops below a critical threshold.
And what's that threshold usually?
It's typically around 20 to 30 psi.
And how does it do that mechanically? What's the logic?
It's a really clever bit of pneumatic logic. The mechanism often involves a pressure sensor, like a little bellows or a diaphragm, that's connected to the oxygen line. This sensor, when it feels enough O2 pressure, holds open a safety valve, which allows the N2O and other gases to flow.
But when the O2 pressure drops...
When the O2 pressure falls below that critical 20-30 psi, the diaphragm collapses, or the bellows retracts, and that mechanically and automatically shuts off the supply valve for the non-O2 gases.
So the flow of N2O is directly dependent on having enough O2 pressure.
It is completely dependent on it.
So if I lose my O2 supply, I immediately lose my ability to deliver N2O.
Precisely. The flow of that potentially hazardous diluent gas is terminated, which prevents a catastrophic hypoxic mixture from being created further downstream.
And at the same time, the alarm goes off.
At the exact same time. The second device, the oxygen pressure failure alarm, is triggered, and this provides an immediate, mandatory, non-resettable auditory and visual warning,
Forcing the clinician to act.
forcing them to recognize the failure and immediately switch to the auxiliary oxygen supply or start manual ventilation with air.
Let's just summarize that whole scenario then. How exactly do these systems behave during a massive oxygen pressure loss event? Let's say the pipeline fails.
The process is immediate and automatic. As that O2 pressure drops below 30 psi, the pressure regulator's output drops. The bellows or diaphragm in the failure protection device senses this
And the alarm goes off.
instantly, usually with a very loud, sustained sound that overrides everything else. At the same moment, the N2O flow is mechanically interrupted.
But you still have some oxygen flow available.
Importantly, yes, the machine usually retains a functional flow of pure oxygen at the O2 flush valve. This lets the operator manually flush the circuit, assuming there's some residual gas in the cylinder. The whole response prioritizes life-sustaining O2 over anesthetic efficacy.
Okay, now for the critical exam distinction. This is where we can earn the maximum points. We need to clearly define what these systems do protect against, and more importantly, what they absolutely do not protect against.
This separation is absolutely vital for a comprehensive answer. They do protect against failures related to a pressure drop.
Such as?
Loss of pipeline pressure, low cylinder pressure because the tank is running out, or a major leak somewhere proximal to the flowmeters. The system reacts perfectly to a loss of mechanical energy in the O2 line.
But the key assumption is that the machine knows what gas is in that line.
Correct, and that is the fatal flaw. They do not protect against the most insidious hazard, cross-connection upstream.
Explain that failure mode.
If the main O2 pipeline in the hospital is accidentally connected to an N2O source, say in a storage room or during installation, the pressure remains high. It's still 50 psi.
So the pressure failure device thinks everything is fine.
It sees adequate pressure and stays wide open. But in this scenario, the machine is physically delivering N2O through the O2 line. The patient gets 100% N2O, and the machine provides no alarm at all because the pressure is fine.
And that limitation highlights why you need the pre-use machine check and the O2 analyzer.
It's the only way to catch it.
Is there a second, more subtle failure mode we should know?
Well, yes. They also don't fully protect against cylinder exhaustion if the O2 pressure stays just above that critical threshold, say at 40 psi, but the actual volume is very low.
Because it's a pressure sensor, not a volume sensor.
Exactly. And while pressure usually correlates with volume in an O2 cylinder, a machine operating on a cylinder right near that threshold, or one that has a slow leak, can go from a safe pressure to a failure pressure with very little warning. That's why we still rely on physically looking at the flowmeters and the cylinder gauges.
The pressure safeguards guard the integrity of the supply line. Now we're moving to the flow control section where the gases are actually mixed. So if the pressure system fails because of a cross-connection, or if the user simply tries to dial in an unsafe mixture, this next system, the hypoxic guard, is the defense layer against that clinical error.
This is the definitive answer segment for that 20-mark question on preventing hypoxic gas delivery. The proportioning system exists for one reason: to guarantee adequate oxygen delivery, regardless of user input. It links right back to that historical realization by Hewitt.
Okay, so define the core mechanism of the proportioning system, or the hypoxic guard.
It's a mechanical or pneumatic linkage that ensures the oxygen flow is always proportional to the nitrous oxide flow.
So it physically stops you from turning up the N2O too high without enough O2?
It does. The system will not allow the N2O flow control valve to be fully opened unless the O2 flow control valve is opened commensurately. It physically or pneumatically imposes a minimum ratio.
What specific ratio and minimum oxygen concentration are we talking about? What's typically ensured?
While the exact ratio can vary a little by manufacturer, the governing principle is that the system guarantees a minimum FiO2 that's well above the physiological danger zone.
And the most common ratio, we should quote.
The most common and illustrative ratio is the 3-to-1 relationship between N2O and O2 flows.
Okay.
This mechanical linkage ensures that the inspired oxygen concentration, the FiO2, is always maintained at or above 25%. The machine mathematically prevents the user from dialing in a concentration below that vital safety threshold.
Let's dig into the engineering specifics. This is that's the top score. You mentioned a distinction between mechanical and pneumatic systems. Can you illustrate the mechanism for a mechanical one?
Sure. In mechanical systems, the control knobs for N2O and O2 are physically linked, often with a chain or, more commonly, a gear train.
Like a bicycle chain.
That's a good way to picture it. The conceptual model to understand is one where the N2O flow valve and the O2 flow valve shafts are connected by gears of different diameters. To get that 3-to-1 ratio, the gear on the O2 valve might have, say, 14 teeth, while the gear on the N2O valve might have 28 teeth.
So the N2O gear turns at a different rate to the O2 gear.
Exactly. This fixed relationship means that when you turn the N2O knob, the flow of O2 is adjusted at the same time, ensuring that 3-to-1 volumetric ratio is maintained.
So even if I try to turn the O2 completely off,
the N2O flow will be mechanically limited to maintain that 25% minimum safety ratio. You can't override it.
how does that contrast with the pneumatic systems?
Pneumatic systems achieve the exact same goal, but they use pressure differentials and valves instead of gears.
Okay.
They often use sensitive O2 ratio controllers that measure the pressure drop across both the N2O and the O2 flow resistance points. If that pressure difference indicates you're trying to create a sub-25% O2 mixture, the system pneumatically restricts the N2O flow until the safe ratio is restored.
So different engineering, same outcome.
Same outcome. Proportional flow.
This brings us to the most important caveat, the common misconception that's often asked in exams, the cross-connection trap again, which we need to analyze in detail.
You must show the examiner you understand the system's fatal flaw. These systems, they're brilliant at protecting against user error in dialing the wrong ratio.
Assuming the correct gas is flowing through the pipe.
Exactly. But they do not and cannot protect against cross-connection.
Walk us through that failure scenario one more time. Emphasize why the mechanical linkage is fooled.
Imagine, due to a severe logistical error, the O2 pipeline is delivering N2O, and the N2O pipeline is delivering air. The clinician dials a 75% N2O, 25% O2 mixture.
A standard mix.
A very standard mix. The hypoxic guard linkage works perfectly. It opens the valve labeled N2O 3 times as much as the valve labeled O2. The machine physically delivers a 3-to-1 mixture.
But the gas itself is wrong.
The gas is wrong. Since the gas coming through the O2 Flowmeter is actually N2O, and the gas through the NTO Flowmeter is air, the patient receives a mixture made entirely of 2 non-oxygenated gases.
N2O and air, which is mostly nitrogen.
It's catastrophically hypoxic. This proves that the proportioning system protects the ratio, but it cannot protect the identity of the gas.
Moving on to the operator interface, the bank of flow meters, this area is all about preventing human visual and tactile error during the actual process of mixing and delivering the gases.
The design here is really dictated by decades of optimizing the user interface to minimize confusion, particularly when it comes to oxygen.
Let's start with the physical layout. Why is the oxygen flowmeter position always on the right?
This is a critical safety standard. The O2 flowmeter is placed downstream of all the other flowmeters, so it's physically to the far right.
And the purpose is twofold.
It is. First, it ensures that oxygen is the final gas added to the fresh gas mixture before it leaves the manifold. But second, and crucially, it safeguards the FiO2 if there's a leak.
How does that placement protect against leaks?
Well, if a leak were to happen upstream of the O2 flowmeter, say at the N2O connection point, that leak would only pull away N2O and air.
Leaving the oxygen flow intact.
Exactly. It leaves the proportional flow of oxygen intact and ensures the patient still gets the necessary O2. If the O2 were upstream, a leak could preferentially pull the oxygen away from the mixture, creating a subtle hypoxic mix that the proportioning system might not detect immediately.
So the downstream placement maximizes the integrity of the O2 delivery path.
That's the perfect way to phrase it.
Beyond just the position, there are also tactile safeguards. How is the oxygen control knob designed for safety?
The O2 control knob is intentionally made to feel different from all the others.
Oh, so.
It's usually larger, often fluted or serrated, and it might project farther outward. This all falls under the general rule of color coding and tactile differences.
So you can identify it by feel alone.
Exactly. Oxygen control knobs are green or white, and they have a unique physical texture and size. This differentiation means the clinician can identify it immediately and confidently, even in dim lighting or during a high-stress, rapid response scenario.
So you don't accidentally adjust the wrong gas flow.
It's all about redundancy, using visual, tactile, and positional cues all at the same time.
We also need to discuss the rapid delivery mechanism that's independent of the main circuit, the O2 flush. What are the pros and cons of this really powerful tool?
The backup oxygen flow mechanisms, especially the O2 flush valve, are essential safety tools.
Then when you press it?
It bypasses the flow meters and the vaporizers and delivers a massive instantaneous flow of pure oxygen,
How massive are we talking?
typically between 35 and 75 liters per minute. And it goes directly to the common fresh gas outlet or the breathing circuit. Its purpose is life-saving. Rapid inflation of a collapsed reservoir bag, flushing the circuit in an emergency, or clearing out anesthetic agents.
But with that high flow, there has to be a significant risk.
Indeed, and the exam requires you to state this limitation. That high flow rate generates very high pressure.
So if the O2 flush is activated for too long,
Or continuously while the patient's circuit is closed or partially obstructed, like during inspiration, or if the APL valve is shut tight, the extreme pressure surge can easily lead to barotrauma.
a collapsed lung.
Pneumothorax, yes. And this risk is especially high in neonates, pediatric patients, or any adult with very poor lung compliance. It's a powerful tool, but one that requires immense caution and control.
All right, let's shift our analysis now to the precision engineering needed for delivering volatile agents. The risk here is twofold, right? Agent selection, putting the wrong drug in, and agent delivery, giving the wrong amount, or too many at once.
Absolutely. And given the very narrow therapeutic window of these agents, the safety here is engineered to be mechanical and completely non-negotiable.
So how do we prevent the wrong agent from being sealed in the first place?
That is the role of the agent-specific filling systems.
The keyed fillers.
Exactly. These are keyed mechanisms attached to the volatile agent bottles and the vaporizer sumps. The fitting is totally unique for each agent. Sevoflurane is different from isoflurane and so on.
So the physical geometry is different.
The size, the shape, the connection points, it all ensures that an isoflurane bottle cannot physically connect to a sevoflurane vaporizer. It's a passive mechanical defense against chemical cross-contamination.
And what about preventing the delivery of multiple agents at the same time?
That's handled by the mandatory interlock systems. This system physically ensures that only one vaporizer can be fully turned on and delivering agent at any one time.
Can you describe that mechanism, the interlock?
Sure. The interlock uses a mechanical rail, or a sort of tongue-and-groove system, that runs along the length of the vaporizer mounting manifold. Okay. When you turn one vaporizer to the on-end position, a physical projection engages, sliding into that manifold rail and physically blocking the control dials of all the adjacent vaporizers.
So it serves a dual purpose.
It does. It prevents multiple vaporizers being on at once, and it also ensures that the vaporizers are correctly seated and tightly aligned to prevent any leaks.
We also need to confirm the correct positioning of vaporizers in relation to the flow meters.
For standard variable bypass vaporizers, they are always positioned downstream of the flowmeters, but upstream of the common fresh gas outlet.
So after the gases are mixed, but before they go to the patient circuit.
Exactly. This precise positioning ensures that the total fresh gas flow rate is established before it enters the vaporizer, which allows the mechanism to accurately calculate and deliver the desired concentration of saturated vapor into that total gas mixture.
Okay, now we have to address the exam critical exception. The case study of the Desflurane vaporizer, the Tech 6 Plus. Why is standard safety engineering not good enough for Desflurane?
Desflurane's physics just demand a completely new approach to safety engineering. The challenge is its extremely high volatility.
Its boiling point is just above room temperature.
It is, just 22.8 degrees Celsius at sea level. So if you used a conventional variable bypass vaporizer, the rapid vaporization needed would cause the liquid to cool down drastically.
Cooling effect.
Exactly, and that would lower its vapor pressure and cause the delivered concentration to drop off significantly. It would be completely unreliable.
So How does the Tech 6 Plus overcome this? And what are the specific numerical safety parameters we must remember for the exam?
The Tech 6 Plus is an electrically powered, temperature-controlled vaporizer. It eliminates the cooling problem by removing the fresh gas flow from the vaporization process entirely.
Oh,
The key safety mechanism is an internal electrical heater that keeps the liquid Desflurane reservoir, the Sump, at a constant temperature of 39 degrees Celsius.
39 degrees.
And this heating creates a constant high vapor pressure of 2 atmospheres, or 1,500 mmHg, within that Sump.
And those numbers, 39 degrees C and 2 atmospheres, are high-yield Viva tracts.
You must know them.
So if fresh gas doesn't flow through the sump, how is the agent actually delivered to the patient?
The Tech 6 Plus is a dual-circuit system. The clinician dials the desired concentration, say 6%. The machine's electronics then sense the total fresh gas flow rate entering the vaporizer.
Right.
It uses that data to precisely inject the required amount of pure, high-pressure Desflurane vapor from that 2-atmosphere sump directly into the fresh gas stream just before it exits the vaporizer.
So it's incredibly accurate.
Highly accurate, and it compensates for changes in fresh gas flow and ambient temperature.
But what about the key limitation, the exam trap related to altitude?
This is crucial. While the system compensates for temperature and flow, it does not automatically compensate for decreased ambient pressure, like at high elevation.
And the anesthetic effect is determined by partial pressure, not concentration.
Exactly. Anesthetic effect is all about the partial pressure of the agent delivered to the brain. Since the Tech 6 Plus delivers a specific concentration of volume percent at high altitude, where ambient pressure is lower, the resulting partial pressure in the alveoli will be lower than what you intended.
So what does the clinician have to do manually to fix this?
The clinician must manually increase the dial concentration at high altitudes to ensure the intended partial pressure, the clinical effect, is maintained.
And that's a known point of human-system interaction failure.
It is. It's a perfect reminder that even the most sophisticated electronics don't eliminate the need for clinician vigilance and a solid understanding of environmental physics.
We are now at the final layer, the patient circuit itself. This stage is about protecting the patient from their own exhaled gas from pressure extremes and ensuring that final mixture is what we think it is.
Right. This area covers both mechanical protection and observational safety features, right up to the patient interface.
Let's discuss the one-way valves.
The inspiratory and expiratory one-way valves in the circle system are just fundamental safety components.
And their role is to enforce.
Unidirectional flow. Unidirectional flow of gas through the circuit and through the CO2 absorber.
And that prevents rebreathing of CO2.
It does. If a valve sticks open or it leaks or it's just incompetent, rebreathing occurs. That leads to hypercapnia and respiratory acidosis, which can significantly destabilize a patient under anesthesia.
How is barotrauma prevented in the circuit itself?
That is the primary safety function of the APL valve, the adjustable pressure limiting valve.
The pop-off valve.
Exactly. It acts as the safety pop-off or pressure relief valve during the manual or assisted ventilation. It's a spring-loaded adjustable valve that vents excess gas to the scavenging system.
So it protects the patient's lungs.
By limiting the pressure rise within the circuit, it protects the lungs from excessive positive pressure, thereby preventing barotrauma, like a pneumothorax or interstitial emphysema.
What about the visible reservoir bag? What's its safety role, beyond just being a gas reservoir?
Its safety role is diagnostic. It gives the clinician immediate, continuous visual confirmation of the patient's spontaneous respiration.
And you get tactile feedback, too.
You do. During assisted ventilation, if that bag doesn't move, it immediately signals a system leak, an obstruction, or apnea. It's a simple component, but it's a vital visual monitor of circuit integrity and patient status.
We've talked about many systems that prevent the creation of a hypoxic mix, but there's only one that chemically verifies the result.
That is the oxygen analyzer, and its importance cannot be overstated.
Why is it so critical?
Because it provides essential continuous electronic monitoring of the final inspired oxygen concentration, the FiO2, right near the patient's airway, regardless of any upstream machine errors.
So even if a cross-connection has bypassed all the other safeguards,
or if there's a massive leak, the O2 analyzer is the only thing that confirms the patient is actually inhaling a safe oxygen level. Its alarm is typically set around 30% FiO2, which gives you a warning before hypoxemia can even develop.
And finally, just to bring it full circle, let's quickly reiterate that historical lesson on airway safety.
Right. Patient safety extends beyond the machine. The sources remind us of Hewitt's development of the airway restorer, a simple oral device.
And that just underscores the point.
It underscores that managing the fundamental issue of airway obstruction, the tongue falling back, for instance, with simple physical adjuncts, is just as critical to patient safety as the most advanced electronic system in the world.
Okay, so we've established that the machine's intrinsic safeguards are all preventative.
They are.
The monitoring systems, on the other hand, are purely detective. This section feels key to demonstrating a full understanding of the integrated safety philosophy.
Modern anesthesia is absolutely defined by this electronic safety net. These monitors act as a mandatory secondary warning system.
Let's detail the necessary electronic alarms then.
Beyond the supply alarms we already talked about, we mandate oxygen failure alarms, that auditory warning of supply pressure loss. Then, pressure alarms.
Which detect both high and low pressure.
Right. High pressure, signaling potential barotrauma or an obstruction, and dangerously low pressure, which signals a disconnection or a leak. And then the vital oxygen analyzer alarms, warning if the measured FiO2 falls below that safe preset threshold.
Now, for the maximum scoring discussion, why must we insist that monitors do not replace the machine's intrinsic mechanical safety systems?
This is the critical distinction between prevention and detection.
Oh.
The machine safety systems, the proportioning, the indexation, they're engineered to be preventative. They make the error physically or mechanically impossible.
Whereas the monitors,
your oximeter, your O2 analyzer, your capnograph, they are detective. They only notify you that an error has already occurred or that the patient is already heading toward a critical physiological state.
use the clinical reasoning from our sources to back that up.
The sources really emphasize that routine monitoring, particularly pulse oximetry, is vital because hypoxemia is the final common pathway to serious morbidity and mortality.
So oximetry allows for earlier recognition.
Yes, and that leads to fewer adverse outcomes. However, if a cross-connection happens, the machine's preventative systems have failed. The O2 analyzer and the pulse oximeter become the absolute last line of defense, detecting the hypoxia only after the patient is already inhaling the dangerous mixture.
So if we only relied on detection,
The intervention would always be reactionary, not preventative. That's why robust engineering must always come before and complement vigilant monitoring.
to get maximum points, we have to show some critical analysis. Where can the safety net actually tear? This forces us to confront the reality that no system is truly foolproof.
Right, identifying limitations shows mastery of the topic. And the fundamental failure mode we've come back to again and again is the inability of these mechanical systems to verify the identity of the gas.
So let's synthesize the details of the situations where these safety systems can fail.
The absolute most critical failure mode is cross-connection upstream. We have to reiterate this.
Because it defeats two systems at once.
It does. When N2O is erroneously put into the O2 line, both the O2 pressure failure protection device, which sees adequate pressure, and the proportioning system, which maintains a perfect flow ratio, are functionally bypassed.
The result is a lethal, unprevented hypoxic mixture.
The machine trusts the labels and the pressure. It can't perform gas chromatography. That single vulnerability is the most potent example of a system failure.
We also have that specific hardware-related trap.
Yes, the Desflurane altitude trap. The Tech 6 Plus, for all its sophistication, requires manual input at high elevations.
Because it maintains concentration, but it can't sense the drop in ambient pressure.
Exactly, so it can't maintain partial pressure equivalence. This is a known, engineered limitation that relies entirely on the human to prevent a dose reduction. If the clinician fails to make that pre-op altitude adjustment, the patient will get a subtherapeutic dose.
Risking awareness.
Risking awareness or inadequate depth of anesthesia. It's a classic example of where human error can creep in despite safety mechanisms.
So what's the overarching defense against all of these limitations?
The final conclusion has to be that vigilance remains paramount. We have to reaffirm that historical dedication to safety that pioneers like Clover taught, the importance of anticipating difficulties and preparing your responses beforehand.
The machine can't eliminate human fallibility.
Or logistical error. The only systemic way to guard against these inherent limitations, especially the risk of cross-connection, is through rigorous, standardized, pre-use machine checks.
Which is a safety system in itself, managed by the operator.
It's an essential one, confirming everything from the Botox seal's integrity all the way to the functionality of the O2 analyzer.
Let's transition all of this incredible information into practical, high-impact exam strategy. For our MD candidate, how do they translate this deep dive into a maximal mark answer for a 20-mark question?
Structure. Structure is the key differentiator between a passing score and an excellent score.
So how should they structure it?
It's a precise flow. You start with that compelling introduction, the purpose, the historical context, the high-yield nature of preventing hypoxia, then immediately state the 6-point classification as your foundational framework.
And then fill it in.
Dedicate the bulk of your answer to developing those 6 points. Give extensive technical detail to the high-yield areas we've discussed, the proportioning systems, the O2 failure devices, and the very specific details of the Desflurane vaporizer.
And crucially,
dedicate a separate, significant section to the limitations and failure modes. Then conclude with the role of monitoring and human vigilance.
what are the mandatory headings the examiners will be looking for?
Use clear, numbered, bold headings that correspond directly to that 6-point classification. 1, gas supply safety. 2, oxygen-specific safety, and so on.
And under each one?
Use succinct subheadings, purpose, mechanism, and be specific, like PIS 25 for O2, 35 for N2O, and critically, add a subheading like exam caveat or limitation to highlight the major vulnerabilities we've discussed.
Visual aids are powerful mark boosters. What diagrams can be drawn to enhance the marks?
Simple schematic drawings are highly, highly valued. You should be able to draw a conceptual representation of the pin index safety system.
Showing the yoke, the valve, and the pin configuration.
Exactly. Show O2 is 2.5 versus N2O is 3.5. And for maximum impact, include a schematic of the Desflurane vaporizer. Clearly label the electrical heater at 39 degrees, the high-pressure sump at 2 atmospheres, and the independent injection port. Contrast it with a conventional bypass flow.
Finally, let's nail those common Viva traps and the safe answers. These are the details you have to deliver confidently under pressure.
Focus on quantifying the technology. The Desflurane traps are extremely popular. A common trap. What is the numerical value of the heated sump temperature in the Desflurane vaporizer? Safe answer: 39 degrees Celsius.
Next trap.
What is the resulting constant vapor pressure created by this heating? Safe answer: 2 atmospheres.
And the subtle but important oximetry accuracy trap.
This one tests your critical awareness of monitoring technology. The trap is: which ubiquitous patient monitor has a major known accuracy issue, specifically at low saturations? The safe answer is pulse oximeters.
And you must quantify the limitation.
You must. You have to say they can read up to 5% higher than the actual arterial saturation in the clinically critical 76% to 90% range. Mentioning that specific quantified uncertainty shows a deep critical understanding that goes way beyond just listing features.
That was an exhaustive and highly specific breakdown. Let's distill this down to the 10 or 12 high-yield take-home points for a rapid review.
Okay, here is the bullet point recap of the absolute essentials.
First, categorical classification.
Structure your answer using those 6 points: gas supply, flow control, O2-specific vaporizer, breathing system, and alarms. That ensures comprehensive coverage.
Next, indexing systems.
PIS with 2.5 for O2 and 3.5 for N2O, and DIS prevent cross-connection mechanically at the source. And remember, a missing Bodox seal risks a high-pressure O2 leak and rapid cylinder exhaustion.
O2 failure devices.
The O2 failure protection device automatically interrupts all non-O2 gas flow when O2 pressure drops below that critical 20 to 30 psi threshold. It prioritizes safety.
Hypoxic guard mechanics.
Proportioning systems, which you can illustrate with the 3-to-1 gear ratio concept, guarantee a minimum FiO2 of at least 25%.
And the hypoxic guard limitation.
Critically, these systems only protect against user error in dialing the wrong ratio. They are completely vulnerable to a catastrophic cross-connection upstream.
O2 Flowmeter position.
The downstream rightmost position of the O2 Flowmeter ensures the integrity of the minimum FiO2 against any upstream leaks.
The O2 flush risk.
The O2 flush delivers a massive 35 to 75 liters per minute flow, which, if misused, poses a severe risk of barotrauma, especially in patients with low lung compliance.
Vaporizer safety.
Agent-specific filling systems and mechanical interlocks prevent chemical cross-contamination and the dangerous delivery of multiple volatile agents at the same time.
Desflurane specifics.
The Tech 6 Plus requires electrical heating to 39 degrees Celsius to maintain a pressure of 2 atmospheres for its accurate vapor injection system.
And the Desflurane limitation.
The Tech 6 Plus lacks automatic compensation for high altitude. It requires the clinician to manually increase the dialed concentration to maintain the correct partial pressure.
Monitoring versus prevention.
Machine safety is preventative. Electronic monitoring like the O2 analyzer and oximetry is detective. Both are mandatory, but detection is the last line of defense after prevention has already failed.
And finally, the oximetry trap.
Pulse oximeters have a known accuracy issue. They can potentially read up to 5% high in that critical 76% to 90% saturation range. So, To conclude, the complexity of modern anesthesia delivery just mandates a redundant, multi-layered safety strategy. It spans from passive physical indexation systems all the way to active electronic monitors. Mastery of these safeguards is crucial, not just for your exam success, but for demonstrating a fundamental commitment to patient safety in your clinical practice.
A perfect summary.
These systems are the boundaries that contain the phenomenal power and the potential risk of the anesthesia machine, and they require human knowledge to complete the loop.
That brings us to our final provocative thought for you to take away. We've established that hypoxemia is the final common pathway to catastrophe, and we know that our most relied upon detector, the pulse oximeter, has a specific documented inaccuracy. In that critical 76% to 90% saturation range, it may read up to 5% higher than the measured arterial saturation.
That is a very clinically relevant blind spot.
So if we rely on alarms set near those lower thresholds, say 90%, how does this inherent potential for overestimation fundamentally alter our clinical vigilance? Does knowing that the number might be lying to us by 5% in the most dangerous zone force us to abandon reliance on the monitor's alarm entirely?
And instead trust our clinical assessment of the patient's more subtle signs of hypoxia.
Exactly. Anticipating the alarm rather than waiting for it to go off.
A question that should drive every MD candidate's clinical practice, and perhaps influence where they choose to set that alarm threshold.
Indeed. Something substantial to mull over until our next deep dive. Thanks for the breakdown.
Always a pleasure.